Assalamualaikum, my name is Nik Nurakila. On lab 6, I'm gonna explain the activity 1 and activity 2. So we start on activity 1. For activity 1 is electrical power measurement in ADC circuit. So we have to construct this circuit, this example circuit on the software. I'm using multi-sim. So first, we have to make sure that this is DC power source and we put the voltage to 60 volt and connect it to the resistor. On this exercise, we're gonna use various value of resistor to measure the different value of power. So this is multimeter. We put it parallel to find the voltage on the load, and this multimeter is to calculate the current. The current, to calculate the current, it should be series with the resistor, and this is the wattmeter. So we try to run it on 500 resistance. So for voltage is 60 volt, and for the ammeter, for the current is 120 milliampere, and for the power is 7.2 watt. And we'll try to change the resistance to 400. So this is the answer that we got. The power is 9 watt. Okay, now we continue with activity 2. Activity 2 is electrical power measurement in an AC circuit with resistive load. So we're gonna construct this example circuit here with using the multi-sim. So this is the AC power source. This is the multimeter, the wattmeter, and the resistor. So first, we need to make sure that we put the voltage peak on 100 volt, and the resistor are varies. We connect it to the resistor. And the multimeter should be connect parallel to measure the voltage. And this is for the current in wattmeter. From the lab sheet, we have varies of resistor from 100 to 500. So we're gonna try to simulate the 500 resistor. And this is the answer that we got for the 500. And we try to change it for 400. And we run it. And this is the answer that we got. Thank you.
Hi everyone, good day. My name is Nityan Raja. My matrix number is CE190043. So today I would like to present about activity 3, which is about electrical power measurement in an AC circuit with capacitive load. So let's we look into the procedure. First, we did a circuit connection, which has been created as shown in figure 6.4 in the lab sheet. So AC voltage supply has been set to 100 voltage peak and 50 hertz for the frequency for each of the load value given in table 6.3. which is in the live sheet, the impedance value has been calculated using the mathematical formulation. So the simulated apparent power and simulated real power has been measured and recorded using the chosen simulation software, in this case which is a Proteus software. So the circuit has been observed and the power factor has been calculated using equation 1. So the equation 1 also is in the live sheet. So let me explain about the calculation for XC and the impedance. So this is the calculation that we did for this manual calculation for this activity 3 experiment. So this is for the XC and this is for the impedance. So these are the values that we obtained from this manual calculation. So let's we look into the simulation for activity 3. So we are in Proteus software. So this is the circuit that we have created based on our lab sheet. So this is an AC source. So let's we look into the parameters. So the V peak we have set into 100. The frequency we have set into 50 hertz. So this is a double pole single throw switch. This is a fuse. So this is the AC voltmeter and this is a wattmeter. So our load is a 100 ohm resistor and a capacitance with 10 microfarad. So let's we simulate based on the table. So for our first experiment, we just set this resistance into 100 ohm and the capacity we will set into 2 microfarad. So let's we run the simulation and let's we look into the value that we have obtained. Okay, for this experiment, the real power that we have obtained is 0.20. So let's we look into the apparent power. So in order to find the apparent power, we just need to change the display range in the wattmeter. So to find the apparent power, we just need to set into VA. So let's we run the simulation again. Okay, as you can see, we have obtained 3.14 apparent power for this simulation. So these values uh, will be uh, will be entered in the table. So this experiment is repeated for 2 microfarad, 4 microfarad, 6 microfarad, 8 microfarad, and 10 microfarad for this activity 3. So that is the simulation that we did for activity 3 in the Proteus. So let's we look into the result. So for load, these are the loads that we have used in our simulation, and this is the impedance that we have calculated using the formulas. From the simulation, we have obtained this apparent power. So the apparent power and the real power from the simulation. For the calculation of power factor, so this is the formula that we have used, and this is the power factor that we have obtained for this activity 3 simulation. So let's we look for the discussion. So based on this activity 3, the value of resistance is constant for all the 5 loads, and the capacitor value has been changed from 2 microfarad, 4 microfarad, 6 microfarad, 8 microfarad, and 10 microfarad. So the resistor and the capacitor has been connected in series, and we can say that the value of impedance reduces when the capacitance value increases based on the calculation. So when we simulate using the Proteus software, the apparent power and the real power produced by the circuit increases when the capacitance value increases. So based on the calculation for power factor, the calculated power factor increases when the capacitance values increases in the circuit. So based on the table, we can say that when the capacitance value in the circuit increases, the value of power factor increases, which demonstrate more efficiency of power in circuit. So that's all for activity 3. So let's we look into the activity 4, which is electrical power measurement in an AC circuit with inductive load. For this activity 4, the procedure is as same as activity 3, but we change the capacitive load with inductive load. So let's we look into the calculation for XL and impedance. So for XL, we have used this formula and we have obtained the value for this manual calculation. For impedance, so these are the calculations that we did, and we have obtained the resistive value and the angle for this impedance. So let's we look into the simulation for activity 4. Okay, so this is the simulation that we have used for this activity 4. So this is the circuit. So the circuit is exact as the same for activity 4. So like activity 3. So it uses the same circuit from activity 3. But the difference is that we have changed the load from capacitive to inductive. So this is the circuit. So let's we look into the amplitude and frequency, all same parameters for all the components. So for inductance, so we have set the value of 0.002 Henry. Okay, so let's we run this simulation. Okay, So as you can see, so this is the result that we have obtained from this circuit. So the real power for this simulation is 49.6 watt. So in order to find the apparent power, so we need to change the display range from wattage to VA. So let's we run this simulation again. Okay, as you can see, we also have obtained the same apparent power for this simulation. So this is for this inductance for 0.02 Henry. So this is the result that we have obtained. So this simulation is repeated for 0.004 Henry, 0.006 Henry, 0.008 Henry, and 0.01 Henry. So the result are all has been entered in the table. Okay, so this is the result that we have obtained from this activity 4 simulation. So as you can see, this is the load that we are using. So this is the impedance that we have calculated and entered in this table. So the simulation, the simulated apparent power that we have recorded from the simulation is all the same value, which is 49.6. For the real power, we have obtained all the same except for load 5, which is 49.5, and the calculated power factor. We did the calculation based on this formula. So this is the power factor that we have calculated and entered in this table. So as you can see, for all these load is it achieves unity except for this load 5, which is 0.998. So it's more than 0.95, which is when we round off, it also will be considered as a unity. So let's we look into the discussion of activity 4. So for activity 4, the value of resistance is kept constant, like activity 3, which is 5 float with 100 ohm. The value of inductance is changed, which is 0.002, 0.004, 0.006, 0.008, and 0.01 Henry. So the inductor and the resistor has been connected in series, and the value of impedance increases slightly. So this one is for load 5 when the inductance value increases. So let's say if the inductance values is increases to 1 Henry, so the value of impedance increases, and we can say that when we use the inductance value, which is 1 Henry, the value of impedance increases with the value of impedance. So when we use 1 Henry, the value of impedance also increase. So when we simulated using Proteus, the apparent power, real power produced by this circuit remains the same from load 1 to load 4, except for load 5, which the power factor decreases from unity to 0.998. So based on table 6.4, we can say that the lower the value of inductance in the circuit, the higher the power factor in the circuit. So that's all from me. So I would like to pass this presentation to my teammate. Thank you.